Hi, this is Stu Schwartz from MasterMathMentor.com. This is Super Free Response Practice AB question number 3. Super free response questions are similar to the typical free response questions in past AP exams. But instead of having the usual 3 or 4 subparts, these will have a great many more. It allows us to use the problem setup as a source of many inquiries that can be taken and allows us to do an in-depth study of the situation. Because of that, many calculus concepts are tested and some reiterated. Doing these will take more than the usual 15 minutes, but by tackling all subparts, you will know what topics you need to emphasize as you prepare for the AP exam. It is recommended that you go to the MasterMathMentor website and download the PDF with the actual problem and subparts. If you don't have a printer available, use a piece of paper for parts A, B, C, etc. This video will just show you the solutions, although you can fast forward at times to bypass the solutions and just show the problems. Problem 3 reads, an hourglass is in the shape of a double cone, as shown to the right. The bottom cone, shown in red, is filled with sand, and then when it is turned upside down, sand will slowly drop to the lower cone, which now is in blue. The device is used as a timer. The red cone is a right circular cone, but the blue cone is not. At height h, measured in inches from the opening in the cone, the radius r, also measured in inches, is approximate for the blue cone and exact for the red cone, and are shown in the table below. And we see our different h's in inches, 0, 1, 2, 3, and 4 inches. And the radius of the blue cone, which again is approximate, is 0.1, 0.3, 1, 2.5, and 4 inches. And the radius of the red cone, which is exact, is 0.1, 1.1, 2.1, 3.1, and 4.1. For this problem, only the arithmetic features of your calculator can be used. Part A reads, write an expression that relates the linear relation of the red cone's radius to its height. This is obvious as r is equal to h plus 0.1. But it is also important because this relationship will be used in other subparts of this question, and it is imperative to get it correct. Just 1 point for getting the formula. Part B asks you to use the trapezoidal rule to approximate the average radius of the blue cone. This problem could cause confusion, because when we think of the trapezoidal rule, we think of area, and there doesn't appear to be any area within the problem. But realize that in the blue cone, there is a relationship between h and r. We're not sure what it is. We have some values, but we don't have the relationship yet. But we do have points, and we can see the relationship in the graph. So when we're asked to find the average radius, we are simply asked to find the integral, which is the area under the curve, divided by 4. So the average radius is 1/4 the integral from 0 to 4 of r blue dh. And that will be 1/4 times, using the trapezoidal rule, 1/2 plus 0.1 plus 2 times 0.3 plus 2 times 1 plus 2 times 2.5 plus 4. And this becomes 1/8 of 11.7, and our answer is 1.462 inches. 2 points for this problem, 1 point for the formula, 1 point for the answer. Part C reads, horizontal planes are drawn perpendicular to the height in the red cone, creating circular areas of sand. Find the average area of all of these circles. The key to this is in the drawing. Even though our cone is vertical, it makes more sense to draw them horizontally, and we will do this for the rest of this problem. So we will look at the relationship r equals h plus 0.1 as y equals x plus 0.1. We then draw a mirror image across the x-axis and create our cone by drawing discs. We see 4 representative discs. We want to first find the area of all these discs, and we use the formula pi r squared. So we will integrate pi, integral from 0 to 4, of r squared dh. Or, if you want to, pi integral from 0 to 4 of y squared dx. We also then have to divide this by 4 to get the average area. So we are looking at pi over 4 integral from 0 to 4 of h plus 0.1 quantity squared dh. Or, if you wanted to, pi over 4 integral from 0 to 4 of x plus 0.1 quantity squared dx. We cannot use the calculator for integration, so we will expand the expression and integrate by hand. We get pi over 4 integral from 0 to 4 of h squared plus 0.2h plus 0.01 dh. Integrating, we get pi over 4 times the quantity h cubed over 3 plus 0.1 h squared plus 0.01 h evaluated from 0 to 4. That gives pi over 4 times the quantity 64 thirds plus 1.6 plus 0.04. And we use the calculator for arithmetic, getting the average area is 18.043 square inches. For this problem, 1 point for the integral and the constants, 1 point for the actual integration, and then 1 point for the final answer. D reads, sand flows through the hourglass from blue to red. When h is 1.5 inches, the radius of the sand in the blue cone is decreasing at the rate of 0.2 inches per minute. Approximate how fast the height of the sand is decreasing at that moment in time. This is a related rates problem, and the relationship we want is dr dt equals dr dh times dh dt. We are given that dr dt equals negative 0.2. In the blue cone, we do not have a relationship of r and r to h. However, we do have some points, and we can approximate at h is equal to 1.5, dr dh is approximately 1 minus 0.3 over 2 minus 1, and that gets multiplied by dh dt. So negative 0.2 is approximately equal to 0.7 dh dt, and therefore dh dt is equal to negative 2/7 inches per minute. For grading, 1 point is given for the relationship for dr dt, 1 point for the approximation of dr dh, and then 1 point for the answer. In part E, suppose sand flows through the hourglass from red to blue. The radius of the sand in the red cone is decreasing at the rate of 0.15 inches per minute. Determine how fast the height of the sand is decreasing at that moment in time. This problem uses the same relationship, dr dt equals dr dh times dh dt. We are given dr dt, which is negative 0.15. In this problem, we are not given a value of h, but we do know what dRdh is because we have the relationship that r is equal to h plus 0.1, and therefore dRdh is equal to 1, and therefore dH dt will also equal negative 0.15 inches per minute. Same grading as in D, 1 point for the relationship for dr dt, 1 point for the value of dr dh, and 1 point for the answer. Problem F reads, if the blue cone is completely filled with sand, use a right Riemann sum to approximate its volume. Show how you got your answer. Instead of rectangles, we will use cylinders of height h is equal to 1. We know that the volume of any cylinder is equal to pi r squared h. So therefore V will approximately equal to pi times the quantity 0.3 squared plus 1 squared plus 2.5 squared plus 4 squared, which is pi times the quantity 0.09 plus 1 plus 6.25 plus 16, getting an answer of approximately 23.34 pi cubic inches. 2 points for this problem, 1 point for showing the formula, 1 point for the answer. Part G reads, if the red cone is completely filled with sand, find its volume. And again, show how you got your answer. Unlike the blue cone above, where we only had points, for the red cone we have a formula. So we could immediately say that V is equal to pi integral from 0 to 4 of h plus 1 quantity squared dh. This becomes V equals pi times h plus 0.1 cubed over 3 evaluated from 0 to 4. And V is therefore equal to pi times 4.1 cubed minus 0.1 cubed over 3 cubic inches. This could also be done without calculus, utilizing the fact that the volume of a cone is 1/3 pi r squared h. Remember though that formula gives the cone from a start of h is equal to 0. And in our picture, we have a cone, but because of the sand having to flow through the bottom, the very, very bottom of it is cut off. So therefore, V would equal pi over 3 times 4.1 squared times 4.1 minus 0.1 squared times 0.1. This gives exactly the same answer, pi quantity 4.1 cubed minus 0.1 cubed all over 3 cubic inches. 3 points for this problem, 1 point for the integral setup, or the volume of a cone formula, 1 point for the integration, or the evaluation of the cone formula, and then 1 point for the final answer. In H, you are told that the blue cone could be modeled by r equals h squared over 4 plus 1/10. If it is completely filled with sand, find its volume. We can see by the graph that the points do a good job of approximating the radius, or perhaps the model, h squared over 4 plus 1/10, does a good job of modeling the actual points. We're not quite sure of which one is accurate. However, the volume, according to this formula, will be pi integral from 0 to 4 of h squared over 4 plus 1/10 quantity squared dh. No calculator use, so we look at pi integral from 0 to 4 of h to the 4th over 16 plus h squared over 20 plus 1/100th dh. 3 points for this problem, 1 point for the integral setup, 1 point for the actual integration, and then 1 point for the answer. Integrating, we get pi times h to the fifth over 80 plus h cubed over 60 plus h over 100, evaluated from 0 to 4, or pi times 1024 over 80 plus 64 over 60 plus 1/25. And we get an answer of the volume is 13.907 pi, or 43.689 cubic inches. I reads, since it is an hourglass, it should take 1 hour to empty the blue cone. Based on answer H, what is the rate that the cone is emptying in cubic inches per minute? This is easy. dV dt will equal 63.689 cubic inches over 60 minutes, or 0.728 cubic inches per minute. It is important to understand here that dV dt is a constant. Even though the radius is changing and the height is changing as the sand goes down, the volume is always 43.689 cubic inches. And since sand will leave the cone at the same rate, dV dt is a constant. Just 1 point for the answer. Question J reads, use your answer in I to determine how quickly the height in the blue cone is decreasing when its height is 2 inches. We leave the answer for part I, 0.728 cubic inches per minute, as dV dt. We first need to have an expression for the volume as a function of h, its height. And we can say that v is pi integral from 0 to h of k squared over 4 plus 1/10 quantity squared dk. We can use any other variable we wish other than k except for h. So dV dt equals dV dh times dH dt. dV dh is the derivative with respect to h of the v function. So it's the derivative with respect to h of pi integral from 0 to h of k squared over 4 plus 1/10 quantity squared dk, and we multiply that by dH dt. We know this to be, by the second fundamental theorem, pi times h squared over 4 plus 1/10 quantity squared. Evaluated at h is equal to 2. So we have negative 0.728, which is our dV dt, equals pi times a quantity h squared over 4 plus 1/10 quantity squared at h is equal to 2 dt, dH dt. And therefore, solving for dH dt, we get negative 0.728 over, plugging in our value of h is equal to 2, we get 1.1 squared pi. Our answer is 0.192 inches per minute. Since you are asked how quickly is the sand decreasing when the height is 2 inches, an answer of 0.192 inches per minute is acceptable. But in reality, dH dt is negative 0.192 inches per minute. We know that dH dt needs to be in inches per minute, but you may be wondering, how do we end up with those units? We can use the fact that dH dt is equal to dV dt over dV dH. dV dt is measured in cubic inches per minute, and dV dH is equal to cubic inches per inch. So using cancellation, we use dV dt is cubic inches per minute over square inches. and this gives inches per minute. 4 points for this problem. 1 point for writing v as a function of h. 1 point for our dv dt formula. 1 point for using the second fundamental theorem of calculus statement, and then 1 point for the final answer. Part K reads, use your answer in Part H to write, but not solve, an equation involving the height K of the sand in the red cone when it is completely filled. We found from Part H that the blue cone, completely filled, has volume 13.907 pi. So we need an equation set equal to that number. Realize that the red cone is defined as h starting at 0 and getting larger to a maximum of 4. But when the red cone is being filled, it's on the bottom. So the bottom limit of our integral is k, not k, but 4 minus k. So our integral will read pi integral from 4 minus k to 4 of h plus 0.1 quantity squared dh equals 13.907 pi. We can drop the pi's and write the integral from 4 minus k to 4 of h plus 0.1 quantity squared dh equals 13.907. Alternatively, we could say that the integral from a to 4 of h plus 0.1 quantity squared dh equals 13.907, and k is therefore equal to 4 minus a. 3 points for this problem, 1 point for the limits in the correct orientation, 1 point for the integrand, and 1 point for equality to the Part H answer. L reads, as sand flows out of the blue cone, the circumference of the sand level decreases. Use the answer in Part J to determine the rate of change of the sand's circumference when h is equal to 2 inches. We know that the circumference of the top disk of sand is 2 pi r, which is 2 pi times the quantity h squared over 4 plus 1/10. So therefore dc dt equals dc dh times dh dt, or 2 pi times h over 2 times dh dt. 2 pi times h over 2 when h is equal to 2 is simply 2 pi. And dh dt is negative 0.728 over 1.1 squared times pi. So dc dt when h is 2 is equal to 2 pi times the quantity negative 0.728 over 1.1 squared times pi, or negative 1.203 inches per minute. Points for this problem: 1 point for dc dh at h is equal to 2, 1 point for using the chain rule, and 1 point for the final answer. M reads, a drop of water works its way down the red cone in the same vertical plane. Write an expression that represents the distance that it travels. No calculus here. We are just finding the distance of a straight line between 2 points. The points are 0, 0.1, and 4, 4.1. Using the distance formula, the distance is the square root of 4 minus 0 squared plus 4.1 minus 0.1 quantity squared, and that turns out to be 4 square root of 2 inches. Only 1 point here for the answer. There are 32 points available for this question. There is no exact formula for what number of points will constitute a 5, 4, 3, 2, or 1 on the AP exam. However, these percentages are what have been used in the past based upon exams released by the College Board. While you can extrapolate for just this question, realize that this question only tests a limited number of AP topics. So it is recommended that you do a number of the super free response questions in this series. Then combine your results, total your points, and then use these percentages to get a feel for how you will do in the AP exam. And more importantly, what concepts you need to strengthen in order to improve your score.